Heisenberg uncertainty principle. What the principle states is that for a set of complementary variables, meaning two variables which are measurements, physical measurements that are involved with each other, there's actually a limit to the precision that you can attain for the combination of the two measurements. One measurement affects the other. And one of the complementary variable sets is the energy time set, in which energy, if you measure energy very precisely, you will know very little about the time frame in which the event is happening. And vice versa, if you measure the time very precisely, you will know very little about the energy of the particle that's actually being studied. This is the outcome of the uncertainty principle. The more precise a measurement is, the worse off the complementary measurement will end up being for that specific observable. And the interesting thing about this is that the multiplication, the multiplication of the two standard deviations, the variation, if you will, of the two variable, the complementary variables, ends up being Planck's constant dividing by 4 pi at the very least. In other times, it might actually be greater than that, but this is the lower limit. This is how accurate you could actually get in terms of these two errors. Another one that we're going to also investigate is the idea of position and momentum being complementary variables, and the errors of those two physical parameters also do affect each other, and they have a lower limit of Planck's constant divided by 4 pi. Okay, so this is the uncertainty principle, two specific examples of it. And I kind of want to emphasize the units. For energy, the typical unit is joules. For time, the typical unit is seconds. And since you're multiplying joules times second, you get exactly the units of Planck's constant, joules times second. For position, the unit is typically the meter, and for momentum, the unit is kilogram meter per second. So if we multiply these two units, we're going to get kilogram times meter squared over second, which is the same thing as joules times second, because joules is kilograms times meter squared over second squared. Multiply that by seconds, and you'll end up with the same units. All right, now to give you an example of how the uncertainty principle manifests itself, I'm going to talk a little bit about particle physics, at least to emphasize the idea of energy affecting time and time affecting energy. Now, there is a nuclear process that you guys will study in future chemistry classes. But in this nuclear process, technically, an electron gets captured by the nucleus of the atom, the radioactive atom to which it belongs to. We call this process electron capture. And I, myself, used to think that the electron was literally being absorbed into the proton, forming a neutron. In the process, it is true that a proton gets turned into a neutron, but when you actually dwell deeper into what's going on with the electron and the nucleus, you find out that there's an additional particle that gets produced along with the neutron, something known as a neutrino. And the interesting thing about this process is that what's actually happening is that the mass of the electron is being given to the proton, thus turning it into a neutron. And the residual particle, they'll call it the massless electron, which now has no charge, is what we call the neutrino, pretty much a massless particle as far as we know. Now, the process itself was theorized to occur via the involvement of a very massive particle, a particle known as the the W vector boson, which allows basically the transfer of mass in charged particles. So technically, you're not actually capturing the electron into the proton. All you're doing is just taking the mass of the electron and giving it to the proton while transforming the electron into a neutrino. This entire process is ushered by the vector boson right here, but the vector boson is a lot more massive than either the proton, the electron, or the neutron combined. So then came the question as to, well, how could you have such a massive particle coming out of nowhere? This completely violates the conservation of mass principle. But the amazing thing about it is that the vector boson is a very unstable particle, and it only lasts for a very short period of time. And it turns out that the period of time by which the vector boson lasts is shorter than the time allocated by the Heisenberg uncertainty principle. So within the error of the time measurement, this particle is allowed to exist because there's a probability of it actually existing within that time frame. If you actually extend the time longer than that, then this will not hold true and you will not see the particle present. But so long as the time of this particle remains short enough, shorter than the actual variance of the time within the measurement, then this particle is allowed to exist and allowed to carry on this weak process of nuclear radioactivity. So I always thought this was kind of phenomenal, that the Heisenberg uncertainty principle pretty much allows for things that otherwise would be counterintuitive in terms of conservation of mass, momentum, and other laws of physics. All right, so, and by the way, this is a picture of actual Heisenberg himself, not to be confused with the other Heisenberg that you guys may have seen in other shows, but I like to notice the similarity of, hats, the attire. And I personally love the fact that, Walter White's, the character, decided to go with his alias as Heisenberg because Heisenberg has this lack of concreteness about the principle, right? There's no real like finite value. It's there's just probabilities of it, and that's kind of what this character represents. It's an alias that very well fits Walter White's character. Anyway, moving on to the position and momentum particles. Here, the idea is that if you try to measure an electron to find out either where it is located or what kind of momentum it has, in the case of position, you can use light that has very short wavelengths, and you want to use short wavelengths so that you actually pin down the actual electron. You could think of the wavelengths as being the distance in respect to the diameter of the electron, and if the diameter of the wavelength is a lot larger than the diameter of the electron, you will basically kind of miss exactly where it is. So you need to make this very small. But the problem is that if you make the wavelength very short, the energy of the light being used is very high. And so by getting this measurement of position very accurately, in essence what you're doing is giving the electron a lot of energy, and because of that you automatically change the kinetic energy of the electron, which itself changes the momentum of the electron. So the mere measurement of the electron changes the possible measurement of momentum of that particular experiment. And the opposite is true. If you were to actually measure the momentum of the electron, what you want to do is avoid giving it way too much energy, because that will affect your momentum measurement. So what that means is that you need to use light of very long wavelengths. But because the wavelengths are so long, which allows you to provide very low energy to the electron, thus keeping your measurement precise, because the wavelength is so long, this is almost like looking for a needle in a haystack. You don't really have a good precision because now your size is a lot bigger than the size of the electron. So the measurement gets affected altogether by that. And this is a complete result of the Heisenberg uncertainty principle. Now this is the theoretical aspect of it all. But let me show you right now a quick example of how you would perform the calculation. It's actually rather simplistic. Let's say that you have an electron with an uncertainty in its velocity of 350 meters per second. What we want to find out is the uncertainty in the position ultimately. Okay? And so what we do is we start with the premise of position and momentum. And we're going to go with the idea that this is going to go as low as it can get, h over 4 pi. We know that the velocity uncertainty is 350 meters per second, and here we're given the mass of the electron as well. So first we're going to solve for the momentum, okay? And the idea is that the momentum is the mass of the particle times the velocity of the particle. And in this case, we're not looking for the momentum itself, but rather the uncertainty in the momentum. So we actually multiply the mass of the electron by the uncertainty in the velocity. And those two together will give you the uncertainty in the momentum, which is 3.16 times 10 to the negative 20 kilograms times meter over second. At this point, we utilize the uncertainty principle to solve for the uncertainty in the position. Specifically, we divide h over 4 pi by the uncertainty in the momentum, and we simply plug in the numbers. 6.626 times 10 to the negative 34, that's the value of Planck's constant, kilogram meter square over second, divided by 3.16 times 10 to the negative 18 kilogram meter per second over 4 pi. This will cancel out the kilograms, partially cancel out the meters and the seconds, leaving you with units of meters. And at the end of the calculation, you should find out that this is 1.67 times 10 to the negative 7 meters. And with that, we have basically concluded this lecture. I hope you enjoyed it. I know some of it can be abstract, but it is kind of an interesting topic, and we'll continue dwelling deeper into this realm in future lectures. For now, that's all for lecture 12.